A very good afternoon, everybody. I am Geeta, and it's a pleasure to welcome you all on behalf of eMobility Plus and First View Group to today's insightful webinar on modeling hydrogen production and fuel cell systems using multiphysics simulation. We are so very delighted to have you join with us today. To begin with, we would like to extend our sincere gratitude to our partner, COMSOL, for their continued support and collaboration in making this session possible. So before we begin the session, it is my immense pleasure to introduce our esteemed speaker for today. We are honored to have Mr. Skanda Prasad, Senior Application Engineer at COMSOL Multiphysics Private Limited, joining us today. Skanda has been a technology specialist at COMSOL's India office since 2023. He holds a master's degree in computational mechanics from the University of Duisburg-Essen, where he also worked as a research assistant. And prior to joining COMSOL, he contributed as a project assistant in the aerospace department at the Indian Institute of Science, Bangalore. With his very strong background in computational modeling and engineering simulation, we are very delighted to have him share his insights with us today. Now, to give you a brief overview of today's session. As we know, fuel cells, electrolyzers, and steam reformers play a crucial role in how hydrogen is produced, processed, and utilized across the energy sector. However, developing and testing these complex systems solely through physical experiments can be both time-consuming and costly, which may ultimately slow down innovation and the broader adoption of hydrogen technologies. This is where modeling and simulation tools become extremely valuable. Through advanced simulation, engineers can better understand how chemical, electrochemical, and transport processes interact within these systems. And these allow researchers and developers to evaluate designs more efficiently during the R&D stage, optimize system performance, and significantly reduce development time and cost. So during today's webinar, Mr. Skanda will demonstrate how COMSOL multiphysics can be used to model various types of fuel cells, including proton exchange membrane, fuel cells, alkaline fuel cells, molten carbonate fuel cells, solid oxide fuel cells. Additionally, the session will cover how simulation can incorporate multiphase flow, heat transfer, thermodynamic properties, and other key physical phenomena to provide a realistic understanding of system behavior. Following the presentation, we will move into a live Q&A session where Mr. Skanda will address questions submitted through the Q&A box. Please feel free to share your questions at any point during the session. We will also be launching poll questions during the webinar. We encourage all participants to take part and share their responses, as this helps make the session more interactive and engaging. With that, it is my pleasure to hand over the session to our esteemed speaker, Mr. Skanda Prasad. Mr. Prasad, the floor is all yours.
Thanks, Geeta. Thanks for this nice introduction. And again, I would like to welcome you all to this session on innovating hydrogen technologies with simulations. So again, there's a high push towards clean energies, and hydrogen being one of the cleanest form of energies, right? So we tend to develop various technologies to either produce hydrogen or in the consumption of hydrogen or even in transport of these hydrogen gases. So in today's session, what we'll do is we'll go through the entire hydrogen value chain. We'll see how simulation helps, and as Geeta mentioned, right? So while developing various technologies or newer technologies, what happens is sometimes there might not be some direct methods, direct measurement methods that we can rely on, in those cases, we tend towards simulations. And these simulations require, or the developed simulation model should be in such a way that it encompasses all the domains from different physics areas. And that is where the multiphysics aspect comes into picture. And during this session, we'll see how exactly various physics aspects that actually uh, mm, helps in developing or understanding or analyzing the systems can be included in these simulations. So, going through the hydrogen value chain itself, again, we can look into the production, storage, and transportation or consumption. So, what I mean by production is once, let's say, you use any reformers or electrolyzers to produce hydrogen, then there you might be looking into how effectively or how efficiently you can produce hydrogen with the developed technology, and later that you will move into storage and transportation. Again, here, right, um, these storage and transportations can be from various domains. What I mean by that is it can be from a very high pressure tank, or it can be cryogenic storages, or you might be looking into a pipeline infrastructure itself. So we'll look into those aspects as well. And finally, the produced hydrogen, right? That has to be put into use, and that is where we look into the fuel cell concepts. Again, there are various fuel cell types that we can look into, from proton exchange membrane fuel cells, solid oxide fuel cells, and so on. So before moving into this particular session, I would like to, or we would like to launch a poll question, wherein we would like to know you all, where exactly or how exactly you are experienced with simulations. We'll be launching a poll question now. Please respond to this. Let us know how familiar you are with simulation tools, and why exactly you are looking into these simulation aspects as well. Probably we'll have this poll question open for like a few more seconds, and I would request you all to actively participate so that I can curate this session accordingly. Again, if you have any comments, right, you can also mention that in the questions tab as well. If apart from this, if you are actually looking into simulations from any different perspective, yeah, even we would like to know what exactly you're looking for. So yeah, if we have a active participation, probably we can have this poll question open for a few more seconds. Yeah, I think we have a good response here. So yeah, Geeta, again, if you can just let us know about how their interests are, please let us know.
Sure.
So again, even in the questions tab, I guess there are uh, uh, various domains that you are from. So again, I believe, or from the poll results as well, right? We can come to a conclusion that like most of you or the audience here are diverse. Some of you have already used simulation software, and yeah, some of you are new. So probably I'll try to keep the presentation a bit more generic as well. So we will go ahead by starting with a very good user story that we have from Toyota. So as you can see on the screen, the user story that I currently have is from Toyota, where they were developing hydrogen fuel cell. So their main aim was to get a uniform distribution across the flow channels. So those are well aware of how this fuel cell development goes, right? There will be flow channels, then you have various electrode assemblies, membranes, separators, all of these things, right? But what Toyota was looking into was optimizing these flow channels that you can visualize here. And what they found out is from the COMSOL simulation results, the optimized design to get a uniform distribution of the flow was quite replicating some of the natural or the structures that exist in nature, such as leaves or lungs, where the flow, due to the inlet, the flow later on gets evenly distributed over the electrodes or in the flow channels. And similar to these, there can be various other case studies that you might be working on. And let's start with the hydrogen production itself. Let's go into various technologies, especially used in hydrogen production. To start with, hydrogen can be produced using several different processes, and all of these can involve complex interactions that can be between chemical reactions or, let's say, fluid flow, heat transfer, or even electrochemistry. So in this particular slide, we can see four important or four well-known technologies that goes into hydrogen production. And again, we can also observe how multiphysics simulation plays a critical role in all of them, starting with the methane reformer. So generally, methane reformers works on a principle of where you have steam coming in along with methane, and there you might be requiring for solving CFD analysis, and along with that, you might be looking into chemical kinetics, reaction mechanisms, and so on. Coupling between those are required here. And when we move on to alkaline electrolyzers, you will be looking into current distributions across your fuel cell or electrolyzer stack. And later on, you might be looking into something like a multiphase flow, especially when it comes to the flow channels in PM electrolyzers, and also in solid oxide electrolyzers. There will be transport of various ions into the solid domain that you might be looking into, and all of these involves multiphysics nature, or multiphysics couplings are required to solve these. And yeah, having a complete look into these multiphysics simulation results would give you more efficient or more cost-effective designs. Similar to this, when you go to consumption part as well, there is multiphysics requirement, or multiphysics plays a key role. And again, after producing hydrogen, right, the next step that we'll be looking into is the consumption of these hydrogen, especially with fuel cells. And these fuel cells generate electricity through these electrochemical reactions, generally between the hydrogen and the oxygen, right? And unlike our traditional combustion engines, fuel cells produce more environment-friendly electricity. What I mean by that is the byproduct here is only water. So to understand how effective that is, what we'll look into is CFD simulations plus electrochemistry plus chemical reaction engineering, quite similar to what we had in hydrogen production as well. And talking more about these fuel cells, especially you have very well-known fuel cell technologies such as PEM fuel cells, which are widely used in transportation. That can be either in electrical vehicles, buses, and also in some cases as a backup power system. So again, these PM fuel cells mainly operate in low temperatures, and they generally start quickly. And but yeah, the challenges that you face are also should be looked into. For example, the water management, or the membrane degradation that occurs in these fuel cells. These kind of concepts should be addressed while you develop these fuel cells, or even the hydrogen production technologies. So again, coming to the lower temperature PM fuel cells, again, commonly used in automotive industries, you might be looking into uneven gas distributions or flooding of these flow channels and so on, right? And later on, you might be looking into an entire stack of fuel cells, either for evaluating your thermal management systems, or let's say you want to create an optimized design, as we saw in Toyota example, or if you look into high temperature PM fuel cells, right, there instead of again to benefit from faster reaction kinetics, wherever you have a very high temperature sources, right, you can look into various bottlenecks such as thermal stresses or long-term durability challenges due to the high temperature that is involved. So for all of these, we would be requiring various multiphysics couplings to perform simulations. And we'll go into all of these one by one, starting from methane reformers, then into the fuel cell part. So before that, again, if I can launch another poll question, wherein if you let me know which exact technology that you are working with, let it be hydrogen generation, using reformer technologies or electrolyzer systems or fuel cells, we would try to focus on that more, and we'll try to again try to showcase the demo on that particular example as well. So I hope you can see the poll questions on your screen. Please respond to this and let us know where exactly or which exact technologies you are working with. So yeah, again, if you are interested in modeling or trying to understand uh, from production till fuel cell systems, you can select multiple options as well, and or else you can mention that in the chat box as well. So once probably we'll have this for a few more seconds, and please respond to this. Later on, I think we can see how many of you are interested in which particular area, and go into or focus more on those devices or those technologies. So yeah, if we have sufficient amount of percentage of attendees responding to this, probably we can look into the poll results and go ahead
Sure.
with the
Shall I
session.
end the poll now?
Yeah, sure.
Can we continue?
Yes, sure. So again, as I mentioned, right here, probably since attendees are from again various domains, we'll try to focus on most of the things. But again, since most of you are from automotive, even this webinar is for automotive attendees, right? We will look into fuel cell demo probably, and we'll go with. But nonetheless, we'll also look into the other technologies. So going ahead with the slide deck here, going into various concepts here, starting from the steam methane reformer. So this methane reformers are currently one of the most widely used method for producing hydrogen. Not only in India or Asia, across the globe, people have gone or people tend to go towards this technology to generate hydrogen. And in this process, methane reacts with steam at high temperatures. Again, it can be in the presence of catalyst to produce hydrogen and carbon, and hydrogen would be produced along with carbon dioxide. Although this is quite widely used, people still face several engineering challenges. So either the issues can be anything like catalyst poisoning or carbon deposition, and it can be also uneven temperature distributions that are actually affecting the reactor efficiencies. So what we'll be looking into this particular example is we'll look into the model definition of how exactly we have built this in COMSOL, and how we can couple various reaction kinetics, various thermodynamics concepts, and fluid flow to understand the setup here. So starting with the model definition, in order to simulate methane reforming, we first define the reactions and the reactor configuration. So coming to the reactions itself, we have both steam methane reforming reaction along with the water gas shift reaction. So these reactions occur inside multi-tube plug flow reactor. So the geometry that you can see on the right hand side of your screen, right, is one such example wherein you have multi-tube reactors, and in each of these reactions occur, and these tubes are packed with porous catalytic material that generally speeds up the reaction process as well. And because the reforming reaction is highly endothermic in nature, meaning it absorbs heat, we generally place furnaces, and in this particular example, you can see a cylindrical domain that is being represented, right? And this represents the heat source or the furnace that provides the required thermal energy. And to analyze the reactor behavior, we have taken two modeling approaches. One is a simplified, perfectly mixed model, and the other is a space-independent model where we consider the geometric effects as well. Starting with the perfectly mixed model, this assumes that the reactants are uniformly mixed within the reactor, and yeah, again, this is a space-independent model, and mainly used for preliminary design analysis. And at the beginning, even from the plots, you can see the reactor at the beginning or at the inlet of the reactor tube, the steam methane reforming reactions are quite active, and that produces hydrogen rapidly. And because of the again the endothermic process, it absorbs the heat as well, and we generally tend to keep this or try to place these heat sources in such a way that we get uniform distribution of hydrogen production across the reactor length. And but in this case, you can see how the temperatures are dipping near the inlet region, and as we go ahead, the temperature keeps on increasing, and later on, these methane is completely consumed, and we can look into how much amount or how much mole fractions of hydrogen has been produced. So this is mainly a space independent model, again for a preliminary kind of understanding. Then later we can develop a space dependent model with the exact reactor designs. And again, here the main thing is we need to look into how earlier we had the assumption that of the geometry not being considered, right? And in this particular case, we can look into more realistic reformers. Probably we can look into the temperature plots as well, how exactly it changes in a three-directional manner, and along with that, how in each regions, how hydrogen can be produced, how exactly the concentration of hydrogen looks as well. Not only these kind of plots can be generated, you can also look into a complete 3D profile of, let's say, one single reactor tube, and you can look into the concentration of hydrogen or the thermal distribution or even the velocity fields that are affecting these hydrogen production itself. So this particular example you can access from the COMSOL websites as well. You can go to comsol.com and try to get access to this as well. So you can go in detail, or you can go through the model in detail. And yeah, if you have any questions, right, you can always post it to us. And moving ahead from this, we have another example that I have taken from the alkaline electrolyzer stack. Again, from steam methane reformer, we'll move into much more cleaner or much greener hydrogen production capabilities. So suppose, let's say there's a large solar farm generating electricity, and that will be high during daytime. And sometimes the electricity produced is more than what the grid needs, right? So instead of wasting this produced energy, we can tend to these kind of alkaline electrolyzer devices or technologies, wherein we supply water, and the extra electricity from the solar farm is used to split the water into hydrogen and oxygen. And the hydrogen can then be stored and later be used for, let's say, fuel cells for any particular electrical vehicle applications, or for any industrial usage as well. So inside these electrolyzer systems, one of the bottleneck or one of the challenges that we tend to face is again wastage of electricity that we take into this electrolyzer itself. So what happens is we have various manifolds and various other region apart from the electrode assemblies, which actually generate the hydrogen, and uh, the given electricity can pass through those unwanted region, and that is what we call as shunt currents, and that can reduce the efficiency of this particular electrolyzer stack. And that is what we'll be looking in this particular model. Again, we'll go into the model definition, how exactly this has been built in COMSOL, how the geometry has been considered. So in this particular image, you can see one single cell, which has been repeated again for 20 times, and each repeating unit cell represents a single electrolysis cell where water splitting occurs. So these cells will be stacked together so that the electrical current flows through all the cells while hydrogen and oxygen are generated. Again, these are again operated at let's say 85 degrees Celsius. But the main focus is main focus in this particular model is the electrical current that are not flowing through these membrane electrode assembly. Rather, let's say some of the electricity goes through these manifolds or the channels, and we'll see how exactly those things can be captured. And for this, you have dedicated interface in COMSOL called again, let's say PM Electrolyzer, and wherein you can combine that with CFD analysis, let's say multi-flow analysis, wherein you look into the manifold geometries and so on. But again, first thing is you will be looking into the current distribution itself. This particularly showcases where exactly these electrolysis reactions are intense. So wherever you have, let's say, high potentials, right, that is where you can decide that you have more intense electrolysis reactions occurring. And coming to the shunt reactions itself, in ideal situation, this stack or the electric current should flow from the power supply through each of these cells that are driving the electrochemical reactions. However, because the electrolyte is conductive, it provides an alternative pathway for the current, as you can see on the screen, wherein instead of going through these cells, it goes through the manifold and bypasses the electrodes. So from this, the efficiency of the system might not be as expected. And talking about efficiency itself in this particular example, what we have plotted is one, we have looked into Coulombic efficiency, and you can see how exactly that can be computed. And along with that, we also look into various other energy efficiencies, and especially with this particular energy efficiency, right, with this particular plot, we have looked into, or we have measured the Gibbs free energy for the production of hydrogen. And yeah, it's highly efficient, especially at the stack current of 1400, and below which again it's not quite efficient. And even if you increase the stack current, we see a trend where the efficiency keeps on dropping. And again, this This is due to the polarization effects that starts to dominate on the later stages. And to get more efficient results, right, what we'll be looking is the shunt currents. Very similar to these graphs, we try to reduce this both at in both near the inlet and outlet regions. What this graph represents is how the shunt currents are across various cells, wherein the cell 1 is near the inlet and cell 20 is near the outlet. And we can see the lower chambers, right, tends to have more shunt currents at the end or at the end of this particular stack. And that is what we'll try to reduce and get much more efficient systems. So now we'll go into solid oxide electrolyzer. Unlike alkaline or PM electrolyzers, solid oxide electrolyzer cell or these systems operate at very high temperatures, typically around 800 degrees Celsius. At these elevated temperatures, the electrolyte is a ceramic material that conducts oxygen ions instead of protons or hydroxide ions, right? So what we'll be looking into is how evenly this particular water that we given or the electrolyte potential, right? How evenly that is being distributed. So what we'll do is we'll set up a geometry with the flow channels. In the previous case, we were not looking into CFD aspect, rather we were looking into how the current passes into the manifold. But in this case, we have added one more layer wherein you can look into the fluid flow mechanisms as well, wherein we have H2O vapor inlet that goes through the electrode or that goes through the channels. And what we'll be looking is somewhat a uniform distribution of the velocity profiles in each channels that leads to uniform distribution or uniform generation of hydrogen. So from this, if we couple that to, let's say, any particular electrochemistry, we can look into the mole fraction of hydrogen that is basically something like a replication of both the densities that we have along with the current distribution. Wherever we have, let's say, high current distribution, or let's say wherever we have a lower mole fraction of hydrogen, we have a high current distributions. And this is due to generation of hydrogen as we go through the flow channels. And from CFD analysis, what we try to get is the density and the dynamic viscosity analysis, wherein this can mainly affect the uniform distribution of the water vapor itself. For example, in this initial flow channel, you see high dense fluid, wherein as you go towards the end or towards the far end of the hydrogen channels, you have less dense fluid. Again, this means that in this region, there's no uniform distribution of the water vapor that goes through the flow channels, and that affects our efficiency as well. The same thing is seen from the dynamic viscosity. Again, wherever we have a higher dynamic viscosity, we can see that more amount of H2O is available for hydrogen production. So these were few examples from the production point of view. Now we'll go into the fuel cell concepts itself, how exactly we can model fuel cells here, starting with a non-isothermal PM fuel cell. So again, from the first example was with just, let's say, current distribution, then we added flow physics. Now we'll add in many more physics such as heat transfer as well, making the flow non-isothermal. And again, these fuel cells can be used in various automotive applications. Suppose you are driving a car, a hydrogen fuel cell car, and whenever you start the car, right, the hydrogen from the tank flows into the fuel cell, and oxygen from the air enters from the other side. So inside the fuel cell, these two react and generate electricity. This powers the electric motor. And what happens is whenever, let's say, you try to accelerate your vehicle, more amount of hydrogen would be pushed in, and we need to analyze the system, how the water starts building up, how the density or how the humidity at any particular section is increasing, that can affect our systems, right? So having more humid membrane can lead to lesser transport of ions. At the same time, if I have a dried out membrane that does not help me in conductivity at all. So it's we must look into the balance between these two, and that is what this particular model showcase. So we have flow channels wherein we given H2 and uh, near the inlet sides, and we have bipolar plates, let's say made up of stainless steel on both the ends, and along with that we have cathode gas diffusion layers, 3 layers of membrane electrode assemblies, and anode gas diffusion layers and the cooling channels around each of these layers. So again, looking into the results, right, starting with um, the potential drops, we can look how exactly near each inlet sections, right, how exactly the potential drop is, and uh, more towards analyzing humidity itself, we'll be looking into the temperature plots. And if you see here in this particular whole cell temperature plot, you can see that higher temperatures are there in this particular end or towards the far end of near the outlet regions, and that affects my humidity, right? And looking into the humidity plot itself, again, that is based from the temperature effects, we can see higher humid present at the far end, and that means that there is higher conductivity or current distribution in the membrane in this particular region. But very high humidity, again, as I told, can affect the transport of ions, wherein at near the inlet itself, I guess here what happens is the membrane can get dried out, and to have much efficient system, this humidity should be more or less uniform across the entire membrane, and it should be in the acceptable amount. So these kind of analysis helps us to understand, let's say, fuel cells or any type of fuel cells, not only these PEMFCs. So now, probably what we'll do is we'll go into the COMSOL software itself. We'll look into a demo of fuel cell stack. We'll look into COMSOL graphical user interface, how we work with it, how all of these are defined. And again, I would like to mention here what exactly I would like to mention here is COMSOL has a unified graphical user interface, wherein irrespective of what physics domain that you are solving for, you would be working with uh, this particular interface itself, and you keep on adding physics from different interfaces. So we'll jump into the software itself. We'll look into how exactly this can be modeled. So I hope everyone can see the COMSOL window upon your screens. And this particular graphical user interface is what you will be working with when you open COMSOL. And here, all the finite element method steps, starting from geometric creation till the last step to visualize your results, would be in this particular interface itself. And on the right hand side, you can see a stack of fuel cell. Again, there are quite a few layers of membrane electrode assemblies, wherein we have separators, we have flow channels, we have cooling channel inlets, and bipolar plates, everything assembled together. And looking into the interior part as well, we have various flow channels for the cooling inlet that are affecting this system. And again, talking or starting with the geometry itself, here in COMSOL, you can either work with creating the geometry in this COMSOL kernel itself, or you can also take in or import geometries from well-known softwares in either standard formats or in some of their native formats as well. Then later on, again, in this particular example, we have built the entire channel or the entire fuel cell stack um, uh, in this particular COMSOL kernel itself. Again, uh, you can later go on through these steps, how exactly to build the geometry, what primitive or what advanced features that we have to build the geometry. Then later, once the geometry is built, we try to assign different materials. Right? Again, each of these domains or each of these geometrical entities may require various different materials. We can add that from the COMSOL material library. For example, the steel AISI 4340, right? This has been added from the material library, and these two bipolar plates have been given this particular material. Then later, we have flow channels, and where we have assigned water material. And along with that, again, any particular electrode material can be given to the membrane electrode assembly. Let's say you want to give different materials for each of these layers, even that can be done. Let's say for membrane, you want to give a different materials for the gas diffusion layer, a different material, GCl, different material. All these things is possible. You can add various materials on top of this and assign for the individual domains. Moving on to setting up the physics itself, COMSOL comes with a dedicated interface called hydrogen fuel cell. A very similar interface is also present for alkaline electrolyzer or electrolyzers. Not only alkaline, even for solid oxide and all of these, you have similar interfaces. Wherein in these interfaces, right, you try to assign each of these domains the respective domain conditions or boundary conditions. So what I mean by domain conditions or boundary conditions, especially those who are new to simulations, what I mean by that is, let's say you have H2 gas phase or gas diffusion layer. You mentioned that this particular layer is my H2 gas phase or the diffusion layer, and if I have any GCl, right, I would mention that membrane wherever the membrane is present, and wherever my flow channels are, I would take in those as well and mention them too. So with this particular interface, hydrogen fuel cell interface, we add various membrane electrode conditions along with current collectors and so on. So you can see how we have assigned diffusion layers for different each individual cells that are stacked in this particular fuel cell. And along with hydrogen fuel cell, we are also solving for porous media flow. Again, Darcy law has been solved here, wherein we have given an inlet velocity, and then we have taken the outlet at the other end. And this can be for both H2 and let's say O2 inlets. And along with that, let's say if there is any cooling channels and if that is free medium instead of porous medium, even that thing can be considered. And on top of hydrogen fuel cell, basically for electrochemical applications, we'll go into much detail later on. But along with that, we have also added heat transfer in porous media. Again, specifying which are my solid domains, which are my fluid domain, what are the inflow conditions. Let's say my gases are coming in at a certain temperature, I would be giving those input values as well. And along with that, there are multiphysics coupling that connects these interfaces. For example, under the multiphysics node, I can see that there's an electrochemical heating that couples the hydrogen fuel cell along with heat transfer in porous media. So whatever temperature effects that has to be included from the heat transfer physics would be directly coupled, and whatever effects that the electrochemistry is giving into the heat transfer is automatically taken. So what I mean by that is there's no need for you to take out the result from one physics domain and put it into other. Rather, these particular couplings takes care of that. And going into detail of, let's say, the electrochemistry itself, starting with the electrolyte definition. And what we'll be defining is, we'll define the electrolyte regions. And one of the key parameters that is required for this simulation is electrolyte conductivity. And once we define the electrolyte phase, then later on we'll be defining, let's say, the H2 gas phase, O2 gas phase. Again, what we require here is mainly the vapor pressures, and or what we'll be using is the vapor pressures and the diffusion coefficients, how exactly my oxygen or hydrogen gets diffused in different layers. And later on, we'll be looking into membrane, how effective these membranes can be by giving in transport coefficients and electroosmotic coefficient as well. Then furthermore, we'll be defining the diffusion layers, especially for my gas transport. Again, I'll be defining my effective electric conductivity and pore volume fractions and the permeability for this porous domains and model it. And in a similar manner, I'll be looking into the O2 gas diffusion layer as well. So apart from these diffusion layers, again, this would be repeated for all of these stacks. And later on, what the main area of interest is the electrodes, where I'll be solving for the electrochemical kinetics, mainly my Butler-Volmer kinetics or Tafel kinetics, right? And what inputs I need to give here is something like electrode potentials, or exchange current densities that I would try to solve for. Once this is set up, again, these electrodes, you'll select all the electrodes that are present here, that are being involved in this particular electrochemical kinetics or electrochemical process. And then later, you go into defining the fluid flow mechanisms itself. In this particular example, a porous media flow has been considered, wherein you take in Darcy law with the porous matrix or the porous medium defining both fluid and giving in the porous matrix. Again, for porous matrix, you will be giving the porosity and the permeability for the porous regions, and along with that, inlet and outlet conditions. In a similar fashion, you would be describing heat transfer in porous medium as well, wherein again you will be considering various or the porosity that you have given in here, along with heat conduction of let's say the porous structure, along with the fluid material that is going inside the porous structure. So with this setup, you would perform or you would compute various study types. Again, coming to COMSOL's study types itself, we have stationary, time-dependent, frequency domain analysis, again, based on what exact problem that you are working with. And not only this, to initialize your system, we have a preset, predefined set of study types. In this case, for initializing your current distribution, you add in those study steps before actually performing any stationary or time-dependent analysis, so that gives you much more better initializations. Not only for electrochemistry, let's say you're working with a turbulent flow, taking the example of steam methane reformers, right? Going back to that, there can be turbulent flow or turbulent regimes wherein you might want to again initialize your wall distance. Again, you will add that particular study type here. And once you add all of these studies, you compute it. You compute the study by clicking on the compute option that you have here. And later on, once it computes, you look into various results. For example, here, let's say I want to look into the temperature effects in different layers. So I'll plot the temperature variables. Either I can create a 3D plot, or I can probe a point and see how exactly my temperature drops over time. But again, in this case, we have done a stationary analysis. But if you do a time-dependent analysis, you can see how temperature drops over time. Or let's say you want to see how temperature is dropping at a particular section. You can draw a line, or you can create a plane and exactly visualize how the temperature profiles are being plotted in the region of your interest. So along with that, probably the main thing is what you will be looking is the temperature in the membrane electrode assembly itself. So as I was talking in the non-isothermal fuel cell example, right? This temperature affects the humidity, and based on this, you would try to create your flow channels in such a way that all of these temperatures are uniform, or the temperature that you get on all of these membranes, right, are uniform in nature, so that you can operate in such conditions wherein the humidity that arises due to this temperature distribution can be controlled. So these kind of analysis can be performed. And again, there are various examples, not only for fuel cells, electrolyzers from production point of view, steam methane, reformers, or if you want to look into just, let's say, multiphase flows, there are various examples of those as well. I'm not going into intricate details of what exact physics interfaces that are there. If you are interested to get to know more about this, right, you can put it in the questions tab. Probably we can take that questions up and try to address that. So yeah, I hope this particular model gives you a good brief understanding how exactly you can work with COMSOL environment, or how you can set up any particular problem in COMSOL. Irrespective of what problem that you have, you would be going into the same interfaces. You would keep on changing these physics interfaces that you add. For example, let's say I want to solve for a multiphase flow. I would go to physics, add physics, and add the required multiphase phenomena that is occurring. For example, let's say there's a dispersed phase mechanism that I want to add. I'll just click on the Euler model or whichever relevant model that I have, and add it to my model builder. So this is how you would be working with COMSOL. And yeah, a quick demo to make you understand how COMSOL works, or how you can define your systems in COMSOL. Again, focusing on the advantages that you have. You add in or import geometries or create geometries here, add materials, go to physics setup with various boundary and domain conditions. Then later move on to uh, let's say visualization part, all in one particular interface with multiphysics aspect being captured. So let's go back to the slide deck, and let's see how further you can optimize your performance. Not only you can just try to understand and analyze your system, as we saw in the first user story as well, right? What we want is we need to optimize these designs. So COMSOL has dedicated module called or dedicated features for performing this optimization. So on top of whatever study type that you add, stationary or time dependent, you add on or you add another optimization study, basically to optimize any particular geometry or parameter and get a much more useful or much efficient devices. So having a look at this, probably I would come to the last poll question now. So right after this session, right, like if you can let us know how you want to proceed further with using the COMSOL. If you want to look into more uh, applications in COMSOL, of course, you can go to COMSOL website, or let's say you want to connect with us further, please select that option. Or let's say you want to use it for any of your projects, you can type in what exact project that you are using. And if you have any questions, again, we can take it now. So please respond to this poll questions. And later on, we'll look into the questions that I guess there are quite a few comments and questions that has been asked in the questions tab. We'll get to that part now once we have answered this poll questions. So again, in the presentation, we saw various uh, uh, from production till consumption part, right? Especially, we did not look into the transportation of this, but let's say you want to look into the transportation, please, transportation or storage, please select the relevant option wherein you want to see examples of those. Probably later on, we can connect with you and showcase those examples as well. And yeah, and yeah, Geeta, if we have sufficient or we have good participation for this poll question, probably we can have this for few more seconds.
All right, I'll just end the poll now.
Yeah, that's so far.
Skanda, you can take it ahead, please.
Yes. Now, probably we can take up the questions that have been asked in the questions tab or the chat box.
Sure.
And yeah.
So the first question is how to couple semiconductor module with electrolyzer or other module so we can be able to simulate electrochemical hydrogen production.
So again, yeah. What in this case, let's say, irrespective of what module you have, how we talk in terms of COMSOL nomenclature is we have various different physics interfaces. let's say you have heat transfer and, for example, let's say a PM fuel cell that has been added in your model. So by default, you have electrochemical heating, multiphysics coupling. But in your case, I guess, photoelectrochemical hydrogen production, there is no direct coupling that is there. What we'll do is, in these cases, for each of these physics interfaces, right, there's a set of variables that are being defined, or that goes into the simulations. So we'll take those variables, put in the boundary condition. Let's say you have some particular electrical intensity from any particular semiconductor interfaces. Let's say you have electric currents interface being added, and you want to look into or taking that particular current into the electrochemistry interface. You'll just take that particular variable, put it in the required boundary conditions, and that is how you can develop a coupled kind of simulation, even when there is no multiphysics or inbuilt multiphysics coupling that is occurring. So yeah, that is how you can tackle your problem. You can couple those using the defined variables.
So we'll come to the second question. It's how can companies benefit for financial assumptions based on the simulation results? Are the output directly captured by investment, bankers for project financial visibility, and techno-commercial evaluation?
So yeah, again, coming to financial aspects, right now, the more the efficient or more efficiency that you have in your systems, right? The example that I took for alkaline electrolyzer, we saw that it is highly efficient in one particular stack current. So let's say you want your fuel cell or your electrolyzers to be defined for different stack currents. What you do is you optimize the design in such a way that you run it for highly efficient currents. And that, of course, changes over time to having more or getting more financial benefits, right? And once you have these developed models, you can pitch in using these simulation results to various investors or various those who are interested, right? They can pitch into various other teams. And one good thing here is that one additional thing that COMSOL offers us, you can easily democratize the simulation models. So an investor might not be looking into or might not be interested in looking into the entire simulation setup, right? So what you can do in those cases is you can create an app, and that particular app can just showcase certain features. For example, the efficiency plot versus the inlet conditions, and that showcases the investor that okay, changing these parameters is giving much efficient systems. So using that app, the investor uh, can make decisions, and that is where the democratization of simulation comes into picture by developing app. And application builder gives you those features. And yeah, probably if you want to know more about how you can build an app on top of let's say any particular simulation setup that you make, and perform and later take it to something like a digital twin application, even that thing can be addressed. Yeah, if you want more information, probably on this we can connect offline, how to build an app and make it or democratize it to those who are not into simulations as well.
So I'll just go to next question. It is, hi, if I do alteration in catalyst composition, can I reflect the same in analysis? PT content, carbon ratio, in honor quality, etc., quantity, etc.
Yes, of course. That is the main purpose of these analysis, right? Let's say you have any catalyst composition being changed, or the available amount of catalyst itself is being changed. Of course, that should be or that will be reflected in the results that you are looking into. And of course, you can do a parametric sweep, or you can have various, let's say, various composition of your catalysts, and you can see or compare how exactly they give any particular results. Let's say in any particular results that you want. Not only in this scenario, in all the simulations, right? Main purpose is to understand or analyze your system for different input values or different compositions or different available materials.
Our next question is, are there separate modules for different fuel cells like SOFC, PEMFS, MCFS, MCFC, or is it just one?
Yes, yes, yes. Yes, of course. That is the main purpose of these analysis, right? Making sure that you have any particular simulation setup that you make,
MCFC, or is it just one?
Talking about the COMSOL product suite itself, we have COMSOL Multiphysics, on which you add, let's say, the fuel cell and electrolyzer module, which gives you capabilities of these modeling these techniques or technologies. And irrespective of which fuel cell or electrolyzer that you are working with, you have um, uh, those interfaces built in. There's no dedicated module for each of, or separately for each of these fuel cell or electrolyzer technology. All of these comes in that particular module called fuel cell and electrolyzer. Yeah, and not only the existing technologies. Let's say you want to have more generic, you do have those options as well. If you want to just solve for any current distributions, coupling with fluid flow, that can be easily done with fuel cell and electrolyzer module itself.
So the next question is, does this has a system level design out available when all the components are integrated for efficiency and performance trend prediction improvement with these changes are done?
If you're talking about process flow, I guess you can address individual concepts, and what we look here in COMSOL is something like a component level simulation. Let's consider a case of production of ammonia itself, wherein you require hydrogen to be produced, and later it goes to ammonia production. Right, a very well-known process is, I guess, Haber-Bosch a process wherein hydrogen is used for ammonia. The entire process can be simulated, but you would be addressing with going into each and individual component individual. So something like a simple model with process flow with just few assumptions is not directly implemented. Rather, you go in detail, you go to component level and solve for that.
The next question says, can we also rough estimate carbon emissions from the COMSOL design tool?
Yes, you can. So for that, again, the reaction mechanisms or the reaction kinetics, the possible reaction kinetics has to be given in. And from that, of course, you can predict how much of carbon emission can be there, or if you want to model any carbon capture mechanisms, even those things can be done. So, yeah.
So our seventh question is from Mr. Sanjeev Mantri. He is asking, is it AI enabled to optimize and achieve uniform reaction temperature and device design?
Okay. So optimization that I talked about in the last slide is from the numerical point of view. Nonetheless, we have something called surrogate modeling, a machine learning technology or machine learning technique. So what it does is you train the model with certain data set, you validate it, then you try to predict for various other case studies. So machine learning has been included, but again, that is either based on the training data that you get from either experiments or from the simulations itself. And the optimization that I talked about is not per se AI, but again, it's a numerical technique that we use. Various techniques are there, various solvers, various algorithms are there, various methodologies can be implemented for this optimization. But yeah, machine learning techniques are implemented here as well. Of course, those things can be used for optimization once you train them quite well.
So we come to the last question. It is by Mr. Anil Murad. He says a PEM fuel cell generates significant of amount of heat generation. How we can optimize this heat generation using COMSOL, and how to use thermal management process?
So yeah, again, in the demo that I showcased, right, that includes cooling channels. And of course, PM fuel cells, they go to, and especially if you are working with high temperature PM fuel cells, that goes to very high temperatures. But let's consider an electrical vehicle example, fuel cell based electrical vehicle. You want to maintain at certain temperature, right? You give a cooling system around that. So you create a geometry for your cooling systems. You solve for your heat transfer and fluid mechanics there, and couple that with electrochemical process. And that is what that particular example or the demo model that I showcased does. And yeah, even in the Toyota example or the user story that I showcased, right, they have looked into modeling flow channels, and furthermore, they will be taking into something like developing those cooling channels around it as well. And that's how you can integrate cooling mechanisms or thermal management systems, not only for fuel cells. Let's say you have electrical vehicles with batteries and all. The same principle holds good. Just that instead of solving for fuel cells, you'll be solving for battery technology there.
So we have one more last question, Skanda.
Mm-hmm.
And we are an early stage startup who wish to start with green hydrogen modeling and simulation. Is
Okay.
COMSOL software freely available for use, and how is it different from others?
So yeah, again, on the licensing and commercial part, probably we need to connect offline, and we'll discuss that. And but again, when you try to compare traditional simulation techniques, what extra COMSOL gives us, earlier you used to do multiphysics coupling in a sequential manner. Let's say a simple case of fluid and structure interaction. You have fluid flow that is affecting any particular structure here. Let's say the flow channels, if you give a very high inlet of your hydrogen gases, that can deform any membranes. Let's say you want to look into those kind of analysis. So what happens there is, once traditionally you would be solving for CFD, then take those results and perform a structural mechanics analysis, right? But here in COMSOL, what you do is you solve both of them simultaneously. So there are chances where, due to the structural deformations, or talking about the electrochemistry itself, the electrochemistry is dependent on the heat transfer or the fluid flow. At the same time, the fluid flow is dependent on electrochemistry. There's a bidirectional coupling that you need to do. Coupled simulation has to be performed, and that is what COMSOL offers. And again, in a unified environment, so that there's no need for you to again take those results, put it somewhere, import it, or let's say you want to add different materials. There's no need to switch to different tabs or different windows to do this. You can just go to previous steps, perform it, or add a new material and come to the next step quite easily. And that ease of going into different steps is what COMSOL offers, along with capturing more realistic scenario with multiphysics coupling. So yeah, that has been seen in the example model as well, right? Like you had heat transfer, gas silo, and the electrochemistry interface, the fuel cell interface being added, and how exactly we have coupled that using electrochemical heating.
That's all with the questions, Skanda. Any closing remarks that you would like to give to our audience?
Yeah, of course. Again, whenever you are trying to develop a newer technology, right, we need to make it more realistic as possible, and that is where multiphysics simulation comes into picture. And as one of you also asked a question, right, like how using these simulation we can pitch to any investors, right, and democratizing these simulations would be quite important. And again, what we try to help with this is the app, where you can create an app on top of these simulation models that helps you to democratize, or let's say you want to share the results to different teams, different organizations, and that's how it is helpful. And always let's try to have multiphysics or more realistic simulations that can be distributed, or that can be easily understood from those who are not into simulations as well. And that gives us a better platform to develop ourselves and also develop this particular technology.
Thank you so much, Mrs. Kanda. That was very, very informative and engaging presentation you have given and explained a lot about how effective it is. And we are sure our audience has gained valuable insights too into modeling hydrogen production in fuel cell systems using multiphysics simulation using COMSOL. And a heartfelt thank you to our audience for your active participation and excellent questions. So as we conclude today's session, we would like to once again thank our partner COMSOL for their unwavering support. And thank you all for joining us and making this webinar a true success. We look forward to welcoming you again soon to another engaging and knowledge-rich session. Thank you. Have a great day.